Prove that for all real positive numbers x, y, and z, the double inequality, this one, holds. For which values does equality hold in the right-hand inequality? This task is presented by Walter Janos. Okay, so first of all, the left part of inequality, that this middle expression is greater than 0, it is basically trivial. We just need to take this expression, make a common denominator, and see that there will be many things. I will write it in a bit. So this middle part, I'll call it middle part equals, yes, the denominator, like x plus y plus z plus 1 times this product, x plus 1 times y plus 1 times z plus 1. And so when we open the brackets here, it becomes xyz plus, and then double, we take 1 out of one bracket and the letters from the other one. So it is xy plus yz plus xz. Then we take all individual numbers, we take 2 ones and 1 letter, plus x plus y plus z. And then we finally take 3 ones plus 1. So it is 8 different things out of 2 brackets. 2 cubed is also 8. And so we subtract this. Brackets are no longer required, but I'll put them x plus what? Y plus z plus 1 overall. So this and this cancels out, and we get this product in the numerator, which is positive, and denominator, which is positive. And so obviously this is greater than 0. So this thing holds. Okay, this is one thing. Now let us consider the other things. If middle part is less or equal than 1 over 8. So how do we do that? The logic is that, look, we see a product x plus 1, y plus 1, z plus 1. What we want to do with this is rather have it some x, y, z. So if we substitute x prime as x plus 1, y prime as y plus 1, and obviously z prime as z plus 1, we can rewrite the middle part in the following way. So I'll just start with the second part. It is over x prime, y prime, z prime, and so x plus 1, so x is x prime minus 1, y is y prime minus 1, z is z prime minus 1, and so therefore it becomes 1 over plus 1 minus 3, so it is x prime plus y prime plus z prime plus 1 minus 3 is minus 2. And this we want, we don't have it as yet, but we want, I'll put a question mark here, that it should be less than 1 over 8. So what do we have? We have x prime, y prime, z prime. It smells already a bit like arithmetic mean, geometric mean inequality. And this kind of smells like arithmetic mean, geometric mean inequality. So let's consider this thing. This thing, x prime plus y prime plus z prime, is greater or equal than 3 cubic roots of x prime, y prime, z prime. And so if we subtract, if we subtract 2 from left and right hand side of this inequality, we get this. What do we see now? We see that this x prime, y prime, z prime, cubic root here, and similar expression is here. So what can we do? We can obviously rename the cubic root, this one, of x prime, y prime, z prime as t. And this t, since x, y, and z are positive, x prime, y prime, and z prime, they are all greater than 1, all of them. So z is greater than 0, z prime is greater than 1. So the product of three things greater than 1, even a cubic root of this product, is still greater than 1. Okay, so this sum in the denominator is greater or equal than something. Therefore, 1 over this sum is less or equal than this something. So this inequality, I'll just rewrite it as middle part, like this middle part 1. And again, middle part 1 is less or equal, basically this thing, less or equal than 1 over 3 cubic roots of x prime, y prime, z prime, minus 2, minus 1 over x prime, y prime, and z prime. And so let's make a substitution. It's equals to 1 over 3t minus 2 minus 1 over, and this thing is t cubed. So our middle part is less or equal than this thing with t's, and this one, we want this to be less or equal than 1 over 2. So if we prove that this thing works, this thing is less or equal than 1 over 8, then obviously this thing will also, since it is less or equal than this thing, then this inequality will hold. Okay, so if we prove it, I will skip several steps. We use common denominator and so on. But after we finish, we get the following expression, that 3t to the power of 4 minus 10t cubed plus 24t minus 16 greater or equal than 0. And t is greater than 1. So the root of this equation, if it is a rational root, could be the factor of 16 according to Horner scheme. And if we factorize it, I will skip these following steps. We see that there are roots t1 equals t2 equals 2. Or the sorry my friends, I forgot the denominator. The denominator is obviously 8 times 3t minus 2 times t cubed. And all of this in a fraction should be greater or equal than 0. So then, what do? We look at the denominator, at the numerator, and we, according to Horner's scheme, its rational root could be the factor of 16. So if we check 2, it works. So for the numerator, t1 equals t2 equal 2. There are two roots of 2, or the root of 2 has the power of 2. So if we factorize, it becomes 3 times t minus 2 squared. And the other two roots, I will just write them. They come obviously from solving the quadratic equation. After we just factorize it, you should know how to do it. So it is t2, t3, t4 equals to negative 1 plus or minus square root of 13 over 3. Okay, so we have t greater than 1. T is greater than 1, then 3t minus 2 should always be greater than 0. This thing is greater than 0. And t minus 2 squared should also be greater than 0. So then we have, let us factorize it. So it is 3 times t minus 2 squared times and so on over denominator, all greater and equal than 0. So, and then look, this thing is a parabola between the roots, one with the plus t4 and one with the minus t3. But if we take even the root with the plus, square root of 13 is greater than 3, so 3 minus 1 is 2 and something over 3 is less than 1. And 1 comes here, and so this has a plus, it is positive. So since t is greater than 1, this thing is also positive. Thus, therefore, all the fraction is positive, greater or equal than 0. Non-negative, at least. And this finishes the proof. So, then if we look, when does equality hold? Equality holds when t equals 2, because they don't really ask for all values when equality holds. But for some values, I'll put here QED because we finished the proof, the fraction is positive. So, and then when equality holds, when t equals 2, then therefore this cubic root of x prime, y prime, z prime equals 2. So we cube this equation, we get x prime, y prime, z prime equals 8. And so the easy thing to make it work is to make x prime equals y prime equals z prime equal 2, obviously. And then we therefore have that x equals y equals z equals 1. So we found at least one value that works. And so let us plug it to equation and see if we actually get 1 over 8. So if we plug 1 here, it's 1 plus 1 plus 1 plus 1, 1 over 4, and this one 2, 2, 2. 1 over 2 cubed, 1 over 8. So 1 over 4 minus 1 over 8 gives exactly 1 over 8. This is when equality holds. And again, this finishes everything.